Hello, my name is Devashish, and today I am going to present our work on aeroelasticity of telescopic morphing UAV wing. So let's start. Unmanned aerial vehicles, commonly known as UAVs, have seen rapid advancement in recent years. An UAV that can be deployed for reconnaissance or airstrike in defense domain, or even agriculture purposes for forestry management in civilian sphere, which could be deployed in variety of purposes, perhaps beyond the line of sight of an area of interest that may be inaccessible. So it need to take off first. Once after takeoff, it may have to cruise to a target location where it needs to be fly slowly to gather information. The mission may call for multiple areas of interest to be investigated, so the aircraft needs to move quickly from one location to other to gather information during its flight time. It needs to return efficiently to its deployment location for recovery. Each section of this flight path has its own design requirements, which demands an unique optimal platform geometry. Wings with large spans provide high range and fuel economy, although they are less maneuverable and have slower cruising speeds. On the other hand, aircraft with low aspect ratio wings are quicker and more maneuverable, but they show inadequate aerodynamic performances. So to solve this problem, we have wing morphing techniques. Wing morphing techniques refers to the change in the shape of the wing during various phases of flight. In conventional aircrafts also, we use localized shape adaptation, typically modification of the airfoil, in order to exert control over the aircraft to provide additional lift during takeoff and landing, mainly at lower cruise speeds. But these wings geometry changes are limited with narrow benefits. But morphing wing with inherent deformability and adaptability can be beneficial for aircraft that operates in different flight regime. An exceptional manuscript by Barberino et al. Shows the detailed study of various wing morphing concepts available in literature. They have broadly classified these wing morphing concepts in various categories we have shown here. Among all of these, plan-form wing morphing techniques are most promising concepts in literature. She et al. In their work highlighted that morphing concepts can be really beneficial by integrating optimal performances in varied flight conditions. Using a number of maneuvers and operating conditions for baseline aircraft, they run an optimizer to maximize the key performance matrices at each design condition, allowing the optimizer to change either just the airfoil of the wing or the platform geometry of the wing. What we can see is that while the baseline vehicle is well suited for certain conditions, but it is suboptimal in other conditions. If we allow the airfoil to morph in flight, it can help to improve the performance in those areas where the baseline is lacking. However, the aircraft that are required to excel in multiple design points sees most benefit from large changes in from geometry, particularly when the design points have conflicting goals. Hence, for an UAV, span morphing is a potential solution which can integrate all these benefits of a high-speed, highly maneuverable, low aspect ratio wing, along with the appreciable range and optimal fuel consumption of an high aspect ratio wing. But there are numerous difficulties for designers in designing the span morphing wing. The development of physical mechanism has been subjected to numerous investigations. In one of our previous work, we also have investigated the morphing-induced dynamical effects of the telescopic beam using a moving load approach. In that study, we have modeled the sliding beam and the aerodynamic loads on it as moving loads. Numerical results shows that the slow morphing speed significantly impacts the dynamic response. In one of our recent study, we have developed a coupled double cantilever beam model for telescopic type mechanism. The morphing-induced dynamic effect of sliding beam, which was not considered in our previous studies, can be considered in this study. In this present study, we have incorporated aerodynamic forces also in the existing model to study the aeroelastic effects. The main objective of the study is to realizing the morphing-induced dynamical effects on the aeroelastic response of a telescopic morphing wing. For the mathematical modeling, a simple unswept, untapered wing is considered in this study. The rectangular wings are assumed to be rigid, but they have rotational springs at the root to provide the flap degrees of freedom. The sliding beams moves over the host beam during the morphing process. The morphing speed in the study we have assumed to be constant throughout the morphing process. The schematic line diagram we can see here. From this, we can formulate the displacement of a general point on both the wings, sliding wing and the host wing. Now, by decoupling both the beams, we can formulate the energy formulations for the telescopic morphing wing as we have shown here. Applying Lagrange's equation for both the generalized coordinates, the dynamic equation of the telescopic morphing wing can be obtained as shown here. For the aerodynamic formulations, we have used quasi-steady aerodynamic assumptions along with strict theory. The work done by the aerodynamic forces over the telescopic morphing wing can be expressed as a summation of the respective host and the sliding wing. The generalized force obtained to formulate the aeroelastic equation of motion. So the equation of motion for the aeroelastic equation can be obtained by using Lagrange equation. The obtained governing equation shows time-varying coefficient terms during morphing process in the matrices. While post-morphing, the governing equation has time-invariant coefficients. So during morphing, the system becomes a time-varying system. The aeroelastic response of the telescopic morphing wing can be obtained by solving this equation numerically. The obtained response for various free stream velocities of air are shown here. The four different phases of morphing process, namely extension process, post-extension process, retraction process, and post-retraction process, are shown here, and they are separated using a dotted line. It can be observed that with increase in free stream velocity, the response of telescopic morphing wing increases. To analyze the response of telescopic morphing wing in various morphing phases, the response of respective phases will look into detail. As we can see, as the extension process starts, both beams starts oscillating with a relatively higher magnitude due to aerodynamic loading, which gradually damped down due to aerodynamic as well as morphing-induced damping effects. This prominent oscillating phase sustains for a longer time period for low free stream velocities. In post-morphing phase, both beams shows transient oscillating response, which gradually decaying to a steady-state response. For low free stream velocity, the oscillatory phase or the transient phase in post-morphing phase observed to sustain for a longer time period. Similarly, we can observe the response for the retraction process for various free stream velocities. Post-retraction process, you can also see transient oscillating response, which gradually decays down to a steady-state response. Same here for low free stream velocity, this transient phase in post-morphing process observed to sustain for a longer time period. Similarly, we have obtained the response of the sliding beam. We can observe that in various morphing phases, the sliding beam dynamics is dominated by the host beam dynamics. The aeroelastic response of the telescopic morphing wing is observed to be highly sensitive to the free stream velocity. But the equation of motion, which we have already derived, suggests that morphing speed will also have an impact on the response of the telescopic morphing wing. Hence, to comprehend the effect of morphing speed on the response, we have simulated the response for various morphing speeds also. The telescopic morphing wing oscillates during extension process with a very high frequency and lesser amplitude for slow morphing speed, whereas for higher morphing speed, the wing oscillates during the extension process with a relatively low frequency and higher amplitude. Post-morphing, both the beams again start to oscillate, which gradually decays down to a steady-state response due to the aerodynamic damping. The oscillatory phase in post-morphing sustains for a longer time period for higher morphing speed. Similar behavior is also observed for the sliding beam also. Here we can see the phase space for various morphing speed and the Poincare section for morphing speed of 0.3 meter per second. The oscillatory response during the extension process observed to be aperiodic, which gradually convert into a quasi-periodic response. For slow morphing speed, the aperiodic response convert into quasi-periodic response very early, whereas for high morphing speed, the response remains aperiodic throughout the morphing process. Post-morphing process, the response trajectory is observed to be attracted by a stable limit cycle. The response becomes quasi-periodic in the steady-state phase of the post-morphing process, irrespective of the morphing speed. So if we want to conclude our work, first we have observed that various mission profiles has its own design requirements, which demands an unique planform optimal geometry. Span morphing is a potential solution which can integrate the benefits of a high-speed, highly maneuverable, low aspect ratio wing along with appreciable range and optimum fuel consumption of a high aspect ratio wing. A coupled double cantilever beam model is developed to mathematically model the telescopic morphing wing mechanism. The effect of free stream velocity on the telescopic wing is studied for various morphing phases. Similarly, the effect of morphing speed is also being studied here. We have also observed the phase portrait and observed that post-morphing process, the response trajectory is attracted by a stable limit cycle. So thank you, and that's all from our side. Feel free to contact us for any further clarifications.